So far in chapter 6, first we talked about looking at one proportion, then we talked about two proportions, then we talked about one mean, then we talked about two independent means. And today we're going to look at how to analyze data from a matched pairs design. And what this really boils down to is we're comparing two groups, just like we did with two independent means, but these groups are not independent like they were in section 6.4. These groups are going to be dependent because they come from a matched pairs design or a matched pairs study. So remember we talked about matched pairs studies back in chapter 1 when we talked about experimental design and sample design and stuff like that. And basically the idea behind a matched pairs study is that we're going to take our subjects and we're going to pair them up so they're as alike as possible. And then within the pair is where we assign the treatment. So the assignment of pairs is not random. We're specifically pairing people up that are as alike as possible. In fact, sometimes a pair could actually be one person that gets both treatments, but in a random order. Or has two measurements taken on them. So for example, anytime we do like a taste test or something like that, then each person would taste both sample A and sample B and give their opinion on it. So when we do that, like our pair is just the one person that's getting both treatments. Because who is more like you than you, right? So another way that they try to find people that are as alike as possible is they look at twins. So a lot of times they'll do twin studies because identical twins, genetically, you can't get any more alike than identical twins. So if they take a set of identical twins and they give one of the twins treatment A and the other one treatment B, then if they see a difference between the treatments, they'll know it wasn't because of genetics because they had the identical genetics. Instead, they'll know it's because of the actual treatment. Sometimes, it might not be twins or it might not be the same person. They just might find people that are as similar as possible, or things like that. What it boils down to is that the assignment, the pairs, like I said, they are not random. Okay, so they're deliberately set. So if I know which people are getting treatment A, then that is going to tell me something about who's getting treatment B because we've specifically matched or paired them up, or it might even be the same individual getting both treatments. So the groups are not independent. Okay, in an independent situation, we take everybody and we randomly assign everybody into the groups, just randomly, flip a coin for every person, something like that. In a matched pairs study, we don't do that. Okay, like I said, we're specifically finding people that are as alike as possible, and then we can randomly assign the treatment within the pair, but the assignment of pairs, not random. So we're going to talk about how to do confidence intervals and hypothesis tests for paired data. And you're going to like this because it turns out we actually already know how to do this. You just don't realize that we know how to do this already, because we're basically doing all the same formulas and everything as we did when we did inference for one mean. It's just now we're going to do it on the differences and call that our one column of data, rather than just having a regular column of data. So data is paired if the data being compared consists of paired data values. So we could have two measurements on each case. We could have twin studies. Each case is matched with a similar case, and one case in each pair is given the treatment, or any situation in which data is naturally paired. So here's an example of a study that they did that we're going to look at. They wanted to find out if pheromones in female tears affected the testosterone levels in men. So they designed this study. They took some cotton pads and they put either real female tears on the cotton pads or a saline solution that had been dripped down the same female's face. Okay, so they had these two treatments. One was real tears and then one was fake tears. And then they had these men and they attached the pad to their upper lip twice. So each man got both the real tears and the fake tears. and then they measured their testosterone level, the male's testosterone level. Okay, so we have these 50 men. Each one is going to get these 2 cotton balls strapped to their upper lip, one with real tears, one with fake tears. And the order that they got those was randomized. And after they've worn the little cotton mustache, I guess, for a while, then they're going to measure their testosterone levels. So this is an example of paired data because the same men got both treatments, right? The same men got both real tears and fake tears. So this is a paired data study. And as we mentioned, our response variable is going to be the testosterone level. All right, so before we look at that study, though, we're going to see if we can identify paired data versus not paired data. So here's kind of a way with that study to show how it might be different. Okay, so if they were separate samples, then we would have some men that got real tears and a separate group of men would get the fake tears. Okay, when we do this, we can list the entire response variable in one column because there's no logical way to match up somebody who got real tears with somebody who got fake tears. There was no purposeful matching going on. But that's not how this study was done. Instead, this was a paired data study because each man got both real tears and fake tears. So in our spreadsheet, when we list out the data, we're going to have one row for each man, and each man is going to have 2 measurements, one for real tears, one for fake tears. So when we actually analyze the data, what we're going to do is we're going to take the measurements for each man and subtract them. So we're going to take the real tears minus the fake tears to get the difference in testosterone for these 2 treatment values. Okay, so here's a chance for you guys to practice and see how well you do identifying paired data versus separate sample data. All right, so for the first one here, to determine if General Mills Lucky Charms tastes better than the generic Target version, 30 students tasted both cereals in a random order and they rated them on a scale of 1 equals yucky to 10 equals yummy. So do you think this is A, paired data, or B, separate samples? All right, you guys did really well here. This one is paired data, which is what 90% of you chose. So it's paired data because the same students are tasting both cereals. So the student would be the pair, and they're getting both treatments, but in a random order. So if I know who tasted the General Mills Lucky Charms cereal, I also know exactly who tasted the generic Target version cereal because it was the same people. Okay, here's another one. A study investigating the effects of exercise on brain activity recruits sets of identical twins in middle age in which one twin is randomly assigned to engage in regular exercise and the other one does not exercise. So do you think this is paired data or separate samples? All right, most of you got this one wrong. So this one is also paired data. Okay, remember, it's paired data if the individuals in each treatment group are matched or paired up. If knowing who's in group A tells you something about who's in group B. And in this case, it says we use sets of identical twins, and one of the twin we had do exercise, and the other twin we had not exercised. So knowing who was in group A tells me exactly who's in group B because it's the identical twin of everybody who was in group A, right? So this one is paired data. All right, next one. Let's see, I've got all my chat windows and everything blocking everything I can't see. In a study to determine whether the color red increases how attractive men find women, one group of men rate the attractiveness of a woman after seeing her picture on a red background, and another group of men rate the same woman after seeing her picture on a white background. So paired data or separate samples. All right, this time 77% of you got this one correct. So this one is separate samples. So we can tell it's separate samples because it says one group of men rate the attractiveness of the woman on the red background, and another group of men rate the same woman after seeing her picture on a white background. So there was no matching or pairing going on. We have this one group of men that rated the red background, and then separately we had a different group of men that were rating the white background. And like I said, there was no matching or pairing going on between the groups. Knowing which guys were in the red background group would not tell us any information about the guys in the white background group, so they are independent from each other. Okay, here's another one. To measure the effectiveness of a new teaching method for math in elementary school, each student in a class getting the new instructional method is matched with a student in a separate class on IQ, family income, math ability level the previous year, reading level, and all demographic characteristics. At the end of the year, math ability levels are measured. So does this sound like a paired data study or a separate sample study? All right, we did pretty good here. 73% of you got the correct answer, which is paired data. So this one's paired data because we specifically are matching these kids up with somebody who's as close to them as possible. So we've got this kid's getting the new instructional method, and then we found somebody not getting that method that was similar on everything we could possibly think of. So similar on IQ, family income, math ability level, reading level, demographic characteristics. So, you know, we found practically their body double in the other class. And so we are pairing them up and then seeing how they do at the end of the year. So that one is matched pairs. So when we're analyzing matched pairs data, then what we're going to do, because remember, we have these two measurements on each pair. So first thing we're going to do is we're going to take the difference within each pair, and then we're going to analyze the differences rather than each column of separate data. So we end up getting this new variable that is the differences, and we're going to do the inference for the difference the same way we would for a single mean. So we're essentially going to use all those formulas that we used in section 6.2 for a single mean. We're going to use those in 6.5, but we're going to use them on the differences. So rather than doing an inference for the difference in means, we're doing inference for the mean difference. Practically sounds the same, I know, but it's a little bit different. When we talk about the mean difference, we're talking about paired data like we are here. So why do we want to use paired data? Why would we do a matched pairs design? And the answer is all of these things. So using paired data decreases the standard deviation of the response. It's going to decrease the chance of a type 2 error for our test, and it's going to decrease the margin of error for confidence intervals. So basically, if we can do this matched pairs study, then because the way that we're doing this, because we're matching people up so that they're as similar as possible, then we're kind of eliminating any effects of like lurking variables that could be impacting our results, right? We're saying, okay, basically the only difference between somebody in group A and this other person in group B is that one of them got treatment A and the other one got treatment B, because everything else is the same about them. They have, depending on what you're measuring, you know, there's the same in every other possible way. So we're kind of eliminating the effect of these other factors that could be influencing the results. So matched pairs studies are very, very common in real life. And they're a very good way to, like I said, to reduce the effects of some of these lurking variables. So they're particularly useful when responses vary a lot from unit to unit. And it makes it so that we can decrease the standard deviation of the response, which in turn is going to decrease the standard error and give us all the good stuff that we want. So let's talk about our formulas for doing these paired data analysis, starting with hypothesis tests. So when we write our hypotheses, first of all, what we're going to have here, if we look at our data, then we're going to have a column with our pair over here, okay? And then we're going to have treatment A and treatment B. And remember, the pair could even be one person. So this could be like a person's name or something. And within each pair, we're going to have a measurement for treatment A. We're going to have a measurement for treatment B. So say those are like 7, 5. Okay, these are just some hypotheticals, okay? And so this is kind of what our spreadsheet would look like. And when we have this paired data, rather than keeping it separate as, hey, this was treatment A and this was treatment B, instead, we are going to compute the differences within each pair, and all of our analysis is going to be done on these differences, all of it, okay? So In this fake scenario that I have here, I'd take A minus B, so 7 minus 5 would give me 2, 3 minus 2 would give me 1, 4 minus 1 would give me 3, okay, and I would do that all the way down. And some of them could be negative, some of them could be positive. It's all good. All right, so then everything I do, I'm going to do on the differences. So my parameter is going to be the mean difference. And when I find the mean and the standard deviation, I'm going to find those of this differences columns. In fact, once I take the differences, I'm kind of ignoring all this other stuff over here altogether. So we're going to write down then what the parameter is and how to write the hypotheses when we're dealing with this paired data. All right, so first let's talk about our hypotheses, and going along with that, our parameter. Okay, so our parameter is going to be mu d, and mu d is going to be the mean difference in whatever the response is. And when you define the mean difference, it's a good idea to say how you took the difference. So, did I take A minus B, depending on what I'm looking at. So for example, we could be comparing prices at two stores. So maybe I'm comparing Walmart and Randall's. Okay, so when I define my difference, I would want to define how I took the difference. Did I take Walmart minus Randall's, or did I take Randall's minus Walmart? And then when I write my hypotheses, my null hypothesis for a paired data study is always that mu d is equal to 0. And we say that because if there's no difference between Walmart and Randall's, then the mean difference would be 0. So the null hypothesis is always that they're the same. And if they're the same, then there's no difference. So the difference is 0. And then my alternative hypothesis is going to be that mu d is either greater than, less than, or not equal to, that's a not equal to 0. For our test statistic, that's what's in the little blue box over here. It's still going to be a t-test statistic, and we're going to have x bar d, SD, ND. These are the mean, the standard deviation, and the number of differences. Oops, I didn't write up high enough. That's okay. Hopefully you can see what I'm trying to say. So XD is the sample mean of the differences. SD is the standard deviation of the differences, and ND is the number of differences, or in other words, the number of pairs. And that test statistic is going to have degrees of freedom equal to n minus 1, or in other words, the number of differences minus 1. And our conditions are the same as we did when we talked about doing inference for one mean, only now everything we're doing is on the differences. So we want all the differences to be normally distributed, or our number of differences to be large. And we're going to check that by looking at a plot of the differences. And if that dot plot or histogram is reasonably symmetric with no extreme outliers, we're going to say it's good. Or if our number of differences is 30 or more, then we're also going to say that we meet the conditions. So like I said, exactly like we did in 6.2, only we're just going to do everything with relation to the differences. For our confidence interval, same idea. Okay, I'm going to have x bar d plus and minus t star times SD over the square root of ND. Okay, that T star is going to have degrees of freedom equal to n minus 1. And remember, T star is based on our confidence level, and the conditions for the confidence interval are exactly the same as the conditions for the hypothesis test. So again, we want the differences to be normally distributed, or we need the sample size to be large. Both of these are going to make it so that when we look at the distribution of the mean difference, that is normally distributed. So let's go ahead and look at this pheromone example a little closer here. For the 50 men, the average difference in testosterone levels between tiers and no tiers was negative 21.7 picograms per milliliter. And the standard deviation of the differences was 46.5. So what they've given us here is they've already found that differences column, and they found the mean of the differences. So this right here is going to be our x bar d. Okay, they found the standard deviation of the differences. So that's our SD. And the number of differences was 50. So that's going to be our ND. So just for your information, in case you're wondering, the average testosterone level before any sniffing was 155. And we want to find out, do female tears lower male testosterone levels? So we're going to figure that out. And then once we figure that out, we're going to figure out a 95% confidence interval for that difference. So starting with our hypotheses and, of course, finding our parameter. So our parameter for a paired data test is always mu D, okay? And mu D is a mean difference, and it's a mean difference in whatever it is that we're measuring. And in this case, we're measuring testosterone levels. So mean difference in testosterone. Okay, and the way that they subtracted is they took tears minus fake tears. So I'm going to put tears minus fake. So our hypotheses, null hypothesis, the mean difference in testosterone, we're going to say is 0. So remember, anytime we're doing this paired data test, null hypothesis is always mu D equals 0. And then the alternative here, we wanted to know, it says, do female tears lower male testosterone levels? Okay, so if I'm taking tears minus fake tears, and I want to know if tears lower testosterone level, okay, that would mean that tears would have a lower level of testosterone. So I'd have a smaller number minus a bigger number. So what kind of number would I get if I took a smaller number minus a bigger number? Would I get a positive number or would I get a negative number? I get a negative number, exactly. So that means for my alternative here, I'm going to use less than, okay? Because if tears reduce testosterone levels, then my mean difference, if I take tears minus the fake tears, would be a negative number. So I'm going to say mu D less than 0. All right, next, I'm ready to check my conditions. So we have, we need either the differences to be normally distributed or the sample size to be large. So either the differences themselves, so either differences are normal or ND is large. And this example came from your textbook. They didn't give us the actual data. They only gave us the summarized data. So we aren't able to do a graph of the differences, but is my number of differences large by our rule of thumb? Yeah, right. 50 is large. It's bigger than 30. So we do meet that. So I'm going to say check, 50 is greater than or equal to 30. So yes, we meet the conditions that way. So we do meet the conditions and we're okay to go ahead and start doing our test. So we're going to calculate our test statistic. Our test statistic is T equal to X bar D divided by SD over square root of ND. Now, you might be looking at this thinking, wait a second, I thought she said that when we do a test statistic, we take our sample statistic minus a null and then divide by the standard error. And that is true. However, as I mentioned earlier, when we're doing the hypotheses, our null hypothesis is always that the mean difference is equal to 0. That means my null value is 0. So that means up here, it would be X bar D minus 0. And if you want to write it up there, that's totally fine. But mathematically, that's not going to change anything. So we usually just leave it off. So that's where in case you're wondering what happened to the null value, that's what happened. It was 0. So we just said, we left it off. So you can leave it off there too if you want. Okay, so now I can plug in my values. So they gave me all these summary numbers over here. So I'm going to get negative 21.7 divided by 46.5 over square root of 50. So getting out our calculators here, I have negative 21.7 divided by 46.5 divided by square root of 50. Okay, don't forget your order of operations here. So we would do all the calculations in the numerator, then do everything in the denominator, then do that division. So if you are trying to plug this into your calculator as one long thing, that's fine. Just make sure that you're putting parentheses around the denominator. Because when you start dividing and then dividing, it actually ends up with a different number if you don't put parentheses around things. All right, so once I do this, I end up with negative 3.333, if I round to 3 decimal places. So negative 3.333. It was negative 3.33266666 repeating. So this here is my test statistic. And we use the test statistic to help us find the p-value. Now, in order to find the p-value, I need 3 things to put into StatKey. Does anybody remember what any of those 3 things are for a p-value? So degrees of freedom, that's one of them. So we need to know degrees of freedom, which in this case is equal to n minus 1 or nd minus 1. So there's the number of differences minus 1. So we're going to have 50 minus 1, which is 49. I wish it was easier to erase on this so that I didn't end up with these ugly things. When I do this in class, it's really easy to just take my hand and scratch it out on the whiteboard, and then nobody has to know. All right, so we need degrees of freedom. We need the test statistic, which we just calculated to be that negative 3.333. And we need to know whether we have a one-sided or two-sided test, or what type of alternative that we have. So our alternative in this case is less than. We have our test statistic. We have our degrees of freedom. So now we're ready to head over to StatKey. So in StatKey, I'm going to tell it that I have 49 degrees of freedom. Then I need to decide based on my alternative hypothesis is going to tell me whether I'm going to click left tail, two tail, or right tail. So if my alternative is less than, I'm going to click on left tail. If it would have been greater than, I would click on right tail. And if it was not equals to, I would click on two tail. Now I put my test statistic here in the bottom box. So that's negative 3.333. And once I do that, then the floating box here is my p-value. So 0.00082 is my p-value. Okay, so 0.00082, I'm going to come back and write that down here. My p-value equals 0.00082. Okay, so 0.00082, that's really, really, really low, right? And when p is low, then HO must go. So our conclusion, we would reject the null hypothesis. Our p-value is super low, so we have pretty strong evidence that exposure to female tears decreases the average testosterone in men. So one thing with these paired data problems is that we can look back at how we took our difference and use kind of that in context in our conclusion. So my alternative was that the mean difference is less than 0. What that meant is that the tears had lower testosterone levels than the fake tears. So the tears reduced the testosterone level. And I can use cause and effect words like that because this was an experiment, right? This wasn't just an observational study. This was an experiment. I think it would be fun to see I always want to know, I always have all these questions when I read about these studies that they post in the book, because I want to know, how did they get all these women to cry? Did they give them a bunch of onions? Did they have them watch a really sad movie? How did they collect all these tears from these women that they then put on these cotton pads and then strap to these guys' upper lips? And I kind of want a picture of the test too, with these guys with these cotton balls strapped to their lip. And I want to know more, how long did the guys have to sit there before they measured their testosterone to see if it was producing anything? And who comes up with these ideas? I mean, these are kind of funny. Probably you guys. You guys are future researchers, and you're going to come up with all these great experiments. So when you do, remember me and write me and send me your data so that I can share it with my future classes, because then that would be super interesting. So next, let's look at how we're going to do the confidence interval. So we decided that yes, real tears does reduce the testosterone levels in men. So now we want to know how much does it reduce the testosterone levels in men. So to do that, we're going to do a confidence interval for the mean difference. So our conditions are the same as they were before. Either the differences need to be normal or the number of differences needs to be at least 30. So we basically already checked those. So we'll put a check mark there again. Actually, we'll put that 50 is greater than or equal to 30 because that's what we did to check those. Next, we need to find T star. Remember, T star is different from T, the test statistic. So T star is different from T, the test statistic. What two things do I need in order to find T star? Yes, the confidence level and the degrees of freedom, right? So confidence level and degrees of freedom. And I believe on the previous slide, it said we wanted a 95%, whoops, there it is, a 95% confidence interval. So that's my confidence level. So I'll put that here. So we want confidence level is equal to 95%. And then degrees of freedom is the other thing that I need. And we already found degrees of freedom on the previous slide, but again, we just took n minus 1, so that's 50 minus 1, or 49. So based on those two things, we can find our T star. So you can use the table if you want. I'm going to go ahead and use stat key this time. And using stat key, I would make sure that my degrees of freedom are in there. Since I just did a problem with 49 degrees of freedom, then I've already got the 49 degrees of freedom in there. Next, I'm going to click on two tail and make sure this top center box has my confidence level in it, which in this case it does. I wanted a 95% confidence interval, and the default that comes up is 0.95. So doing those two things, then my T star is this number on the bottom right, which is 2.010. So I'm going to use T star 2.010. So my T star 2.010. All right, now I'm ready to calculate my confidence interval. So my formula for that is going to be x bar d plus and minus T star times SD over square root of ND. And who remembers what this quantity is called? The SD over square root of ND. That has a special name. What do we call that? Yeah, SE, that's the standard error, right? So if something in the Wiley Plus homework just asks you to find the standard error, then you can be like, oh, I totally know what that is. That's just SD over ND. All right, so now I can plug in everything that I know. So I'm going to have negative 21.7 plus and minus 2.010 times 46.5 over square root of 50. So working out these numbers here, I'm going to take the 2.010 times 46.5 divided by square root of 50, and I get 13.218. So I get 13.21794706. So now I'm going to take negative 21.7 minus 13.218. So negative 21.7 minus 13.218, which gives me negative 34.918. And then I'm going to take negative 21.7 plus 13.218, and I get negative 8.482. All right, so this is my confidence interval. So here's my confidence interval. So now I just need to interpret that confidence interval. So I interpret this just like I interpret all the other confidence intervals that we've been doing so far. So we'd say we are 95% confident that and remember, we're looking at this mean difference, and we took tears minus fake tears. So we could say that real tears reduce men's testosterone levels between 8.482 and 34.918. And I think it was like picograms per milliliter on average. And if you said that we are 95% confident that the mean difference between tears and no tears is between negative 34.918 and negative 8.482, that would also be correct.
Do you think your pulse rate is higher when you're taking a quiz than when you're sitting in a lecture? The data in Table 1 shows pulse rates collected from 10 students in a class lecture and then from the same students during a quiz. The data are stored in the file Quiz Pulse 12. So this is an example of paired data or dependent data because we measured the pulse rates on the same students during a quiz and also during a lecture. So because we took the two measurements on the same student, that's what makes this a matched pairs design, or in other words, we have dependent data. And the appropriate way to analyze a matched pairs design is by first calculating the differences within each pair and then using the mean and standard deviation of the differences like we would with a one sample mean procedure. So here's our formula sheet for chapter 6, and down at the bottom is the matched pairs formulas, but you can see if I look at the formula here for my test statistic for matched pairs, it's almost identical to the test statistic for one mean. So once we compute the differences, we are essentially just going to treat it as if it is a one mean problem. So back here, I would first find the differences within each pair. So for student 1, I would take 75 minus 73. That gives me 2. 52 minus 53 is -1. 52 minus 47 is 5. Okay, et cetera, et cetera. I would do that for all 10 students. And then I want to find the mean of those differences and the standard deviation of those differences. One common error that a lot of students make is they want to, just like we're subtracting within each pair to get the differences, they sometimes think they can just subtract the means and subtract the standard deviations to get the mean of the differences and the standard deviation of the differences. Now, mathematically, it does actually work out that the mean of the differences is the same as the difference of the means. Kind of sounds like a tongue twister, right? So if I take 68.8, doing this on my calculator, so 68.8 minus 66.1, then I get 2.7. And as we're going to see in a second here, that actually is the mean of the differences. So it works out to subtract the means, but it does not work out to subtract the standard deviations. And you can probably see that here. If I take 12.5 minus 12.8, I would get negative 0.3, which is not even a valid value for the standard deviation. To find the standard deviation of the differences, we're going to have to use either Excel or StatKey. So to do that, we're going to open up the data set in Excel. So in Wiley Plus, you can click here for the data set. When you do that, then that will bring up the data file list for our textbook. You would scroll down to where it says Quiz Pulse here, and you can download either the CSV or the Excel file. Then you're going to go ahead and open that up in Excel. So here's what it looked like when I opened that up in Excel. It's got the students, their quiz pulse, and their lecture pulse, just like we saw in the table from the problem itself. Now, in order to do the analysis, what we need is the differences. So I'm going to create another column here. I'm going to call it diff, and I'm going to remind myself how I'm taking those differences. So I'm going to take quiz minus lecture. So I'm going to put that in my header just so I remember what I did. And then I'm going to actually calculate that difference. So I want it to take 75 minus 73. So if I hit equals and then I click on that cell B2, hit subtract, and then click on the C2 cell, that'll give me that difference there. And now I want it to do that for all of the students. So if I click on that first cell, now that I have that formula in there, if I bring my cursor down, watch till the cursor changes to just a different type of plus sign. You can kind of see that there. If I double click on that corner, it will just copy that formula all the way down for me. And now I have all the differences. Once I've calculated the differences, that's really the information I need. I can ignore everything else once I've calculated those differences. Now, as we saw in the formula, what we need are the mean and the standard deviation of those differences in order to find out our test statistic and our p-value. So you can copy and paste this data into StatKey, into the descriptive statistics for one quantitative variable, and have stat key calculate the mean and standard deviation. Since we've already got the data open in Excel, I actually think it's a lot easier just to do it in here while we're here. So I'll show you how to do that. So first I'm going to look at the mean. So the mean is the same thing as the average. In Excel, they just call it the average. So I'm going to type average, and I just want the regular average here. And I want it to find the average of these differences. So I'm going to put that in there. All right, so the mean of all those differences was 2.7. And remember, that is what we saw on the previous slide when we took the difference of the means. So in that way, that's pretty handy that it works out that way. Now we're going to find the standard deviation of the differences. So I'm going to hit equals again, and then I'm going to start typing in standard deviation. Notice there's a lot of options for standard deviation here. I want to choose the one that says for a sample, which is this STDEV.S here, okay? And once you select the correct formula, if you hit tab, it finishes typing out the rest of the formula for you. Okay, now it's got the parentheses there. It wants to find out what do I want to take the standard deviation of, and I want it to take the standard deviation of those differences again, so I'm highlighting those. And then I'm going to put another parentheses on the other end, and I can see that my standard deviation is 9.93367. So if I rounded that to 3 decimals, that would be 9.934. So that's what I'm going to use in my calculations. All right, so back to my problem here. I did already write out my hypotheses here. When we're doing a paired data test, like we are in section 6.5, then our parameter is a mean difference. So in this case, and I'll write it up here, the parameter is mu d. I put the d subscript to remind me that I'm doing a mean difference. So it's the mean difference in pulse rates. So mean difference in pulse rate for a quiz versus a lecture. Okay, if there's no difference in the pulse rate for a quiz and a lecture, then the mean difference would be 0. So no difference is 0. So our null hypothesis is that the mean of the differences, or the mean difference, is equal to 0. And for my alternative, we wanted to know if the pulse rate was higher when we were taking the quiz. And since we did quiz minus lecture, if we got a positive number for that difference, then that would mean that the quiz was higher. So my alternative is that the mean difference is greater than 0, which would indicate that my pulse rate was higher during the quiz. So that's going to be my alternative hypothesis. All right, now I'm ready to go ahead and find the test statistic and the p-value. So here's my formula. This is straight off the formula sheet. And here's the mean of the differences and the standard deviation of the differences that we found using Excel just a couple minutes ago. And the number of differences I have is equal to 10. So when we're looking at sample size, we're looking at the number of pairs in a paired data design. So now I'm going to take these numbers and I'm going to plug them into my formula here. So I have 2.7 divided by 9.934 over the square root of 10. And when I put that into my calculator, I get t is equal to 0.869. And in Wiley Plus, this one tells you to round to 2 decimal places. So if you're doing that, you would get 0.86 for your 2 decimal places. All right, so now I need to find the p-value. And in order to find the p-value, because I'm dealing with a t distribution, then I need to know how many degrees of freedom I have. So as we can see in our formula sheet, t has degrees of freedom equal to the number of differences minus 1. So in this case, that would be 10 minus 1, or 9 degrees of freedom. Now I'm going to go to stat key to help me find that p-value. In stat key, I'm going to come down here to theoretical distributions, and I'm going to choose the t. It's going to ask me how many degrees of freedom I have. I just found out that I have 9 degrees of freedom, so I put in 9 there. Once in here, I am going to click on right tail because my alternative hypothesis said greater than. If my alternative hypothesis would have been less than, I would click on left tail. And if it was not equals to, then I could click on to tail. So I've clicked on right tail because my alternative was greater than, like I mentioned. Now I need to put in the value of my test statistic down here. So I'm going to click here, and my test statistic was 0.859 or 0.86. So I put in my test statistic down there. Once I've done that, this little floating box is my p-value. So my p-value is 0.206. All right, so now I've come up with my test statistic, my p-value. A p-value of 0.206 is actually high, especially if you're using an alpha of 0.05. When p is high, then we keep the guy. So in other words, we're going to fail to reject. So we fail to reject the null hypothesis. We do not have sufficient evidence that pulse rates are higher on average when taking a quiz versus sitting in a lecture. So hopefully that helps you out a little bit when you are dealing with these paired data problems.